Imagine you have a complex decision to make that's very important. You can ask two friends, Bluster and Prudence, for advice. Bluster always tells you what he thinks is the right answer, and even gives you reasons why he thinks he's right. Prudence, in contrast, doesn't ever really give you an answer. Instead, she asks you what you're proposing to do and then provides feedback, evidence for and against your proposed decisions. If you then propose alternatives, she continues to provide feedback on these, but she never gives you an answer. Which of these two would you prefer if you had a complex decision to make? In a recent informal survey I conducted during a talk at the Australasian AI conference, showed that just 3 out of over 100 people in the audience preferred Bluster. The remaining 100 plus people preferred Prudence. I think this is because Prudence helps us to find strengths and weaknesses in our own thinking and gives us control over which options we choose to explore, things that are key to good expert decision making. Despite this preference, the current model of explainable AI-assisted decision support gives us Bluster instead of Prudence, right? These AI decision aids are designed to tell us what they think is the best answer and then explain why that is considered the best answer, in fact trying to persuade us that it's the best answer. This is what MD Sean Coon described to me as a recommend and defend approach. I call this a recommendation-driven explainable AI. This recommendation-driven approach has 2 issues. Firstly is that people find it difficult to determine when they should rely on the recommendations. This often leads to either over-reliance, where people rely on recommendations when they're wrong, or under-reliance, where they don't use them when they probably should. The second issue is control. These recommend and defend approaches inherently focus the decision loop on the decision aid and the machine, reducing the decision maker's locus of control and ultimately probably leading to lack of engagement. In my FACT 2023 paper, I proposed that explainable decision support should look more like Prudence. Instead of recommending outcomes and justifying them, decision support should focus on helping decision makers to find the evidence they need, evidence that can be used to support or refute any hypothesis they want. And importantly, I argue that decision aids should not necessarily provide recommendations at all. I call this hypothesis-driven approach evaluative AI, because instead of explaining decisions, it helps us to evaluate our own decisions. A good human decision maker should do quite well on tasks. However, in some cases, we can actually get AI models that can produce more accurate results, or perhaps as good results more quickly than a human. The goal of AI-assisted decision support is that if we put the human and the AI model together, they should outperform both. Why? Well, it's what we discussed earlier. It's difficult to calibrate when we should rely on decisions and when we should ignore decisions. Let's look at how we got to where we are today. AI decision aids came from the idea of automation. Initially, we built AI systems that could do stuff automatically, but we realized pretty quickly that for some decisions we need humans in the loops. So the straightforward solution was, when we had a decision maker, we could use a machine to give the decision maker some form of answer, and they would use this to help make better decisions. However, the assumption that people would pay attention to recommendations was largely incorrect. What was the solution we came up with? Well, explainability. We could give people information to let them understand why decisions had been reached. The assumption was that this would enable people to calibrate their trust and reliance better, leading to better decision making. However, it seems that this model doesn't work in many areas either. The assumption that people will pay attention to explainability information has proven largely to be incorrect. What are we missing? It's my view that the key part of what we're missing is called self-explanation. Research and development of interpretable and explainable AI has focused a lot on the interaction between the decision maker and the decision aid. Now, this is good because this interaction is important. However, I'm going to argue that we haven't focused enough on a second loop of explainability, which is the internal cognitive process that's ongoing in the person's mind as they aim to make a decision. This is known as self-explanation. In the middle line, the person's trying to understand how the machine reached a particular decision, but also they themselves are trying to make a decision using information they've gotten from that machine. This self-explanation is best modeled using the process of abductive reasoning. So let's focus on abductive reasoning and its relationship to self-explanation. The process of abduction looks like this. First, we observe an event, usually an event that we didn't expect to happen. We then come up with a set of hypotheses that it could explain why that event happened. We judge the plausibility of those events by looking for evidence or observations that can support the different hypotheses. And eventually we can resolve an explanation to our satisfaction. And finally, we might extend that explanation when we receive new data. In this paper, I argue that it's this process, abductive reasoning, that we should support in decision support systems. So what would the requirements of a good decision support system look like to support abductive reasoning? Well, if we want to support the first step, observing in events, then we should design our decision aid interfaces to make it easier to determine what has happened. And we should design interfaces perhaps to highlight unusual events, which are the things that typically need explaining. To generate hypotheses, we could help construct likely hypotheses. For example, given dozens or perhaps hundreds of possible diagnoses for a clinical task, help to construct which are the likely hypotheses given the data that we've viewed. This reduces the set of hypotheses a decision maker has to consider. To support judging plausibility, we could explore how causes affect outputs and help people to find evidence that supports and refutes different hypotheses. To resolve the explanation, we can identify and record important information so we can return to it later or use it to justify our decisions. And to extend the explanation, we can support hypothesis revision and support interactive exploration. I argue that the field of decision support and explainable AI in particular has focused a lot on allowing people to judge plausibility. However, this support is primarily used just to judge the plausibility of the machine recommendation. In my fact paper, I argue for the framework called evaluative AI, which aims to support this process more comprehensively. In evaluative AI, the decision maker can ask questions about particular hypotheses, and the evaluative AI tool provides evidence both for and against the hypothesis they select. They can ask questions about other hypotheses. Further to this, when they see this information, I argue that the evaluative AI framework encourages a feedback loop. Receiving evidence for and against certain hypotheses gives the decision maker ideas about other hypotheses which they can question as well. Let's have a look at an example to make this more concrete, using an example of skin cancer identification. On the left, the decision aid highlights the most likely hypotheses using bold text. If the decision maker has the evidence in the top part of the image here, they might think that this could be basal cell carcinoma. If they click on basal cell carcinoma, they get evidence that supports their hypothesis, the lesion location, color, the fact that it's scarred and bleeding, but also some evidence that might suggest that it's not a basal cell carcinoma. If the decision maker then thinks maybe there's a chance this could be melanoma, they could select melanoma and they would get a different set of evidence. We can see here that the hypothesis has changed and therefore the evidence for and against has changed. But importantly, the decision aid here is not giving the decision maker a recommendation. This framework is different to the current recommend and defend approaches seen in explainability. For example, consider a contrastive explanation model. While it looks similar that we can query different hypotheses, usually the evidence that's given back is an attempt to persuade us that the machine hypothesis is correct. For example, as we can see here, the standard contrastive explanation gives evidence for the machine's recommendation and evidence against all other recommendations. This is a persuasive approach. So this leads to the question, is explainable AI dead, as it says in the title of my paper? Well, I don't think it is. First, there are many applications where the current model of explainability is useful. Consider autonomous systems, where decisions really are made autonomously, independent of a human. However, explainability might be useful to coordinate behavior between people and autonomous agents. Another area is when we have to make decisions at scale, such as cybersecurity threats, where an analyst has hundreds or thousands of threats to deal with each day and a large percentage of them will be classified autonomously, but explainability will be useful for them. Second, any evaluative AI solution needs underlying decision-making models like machine learning, and these models will often be in the format of explainable and interpretable AI. Finally, evaluative AI is explainable AI. The tools and techniques that we have already will help to form part of new evaluative AI solutions. Evaluative AI is really just a framework for thinking about how to apply these tools and techniques better to support decision-making. The existing recommend and defend model that we see for explainable AI for decision-making may be dead as we currently know it, but long live explainable AI.